Hello students, today we're going to be taking a look at section 1-4 entitled Literal Equations and Formulas. We're going to jump right in. There is a model and discuss scenario that I would like you to take a look at. At some point we are going to, in any given lesson, take a look at how it would apply, not just obviously in a word problem situation, which we've seen off and on, but more specifically taking this exact problem and applying it in the way that we have learned and carry it over into a discussion during a live lesson. So we're going to go ahead and jump in with example 1. Rewrite literal equations. Janet wants to calculate the time it takes to earn a certain amount of interest on a principal amount in an investment with simple interest. What equation can she use? Okay, so what we're going to go ahead and take a look at to kick things off is some kind of notation, but also some definitions. So as we can see, I've scrolled down for you just to highlight what is important. A formula, and you guys have worked with formulas many times, right? A good example of a really important formula that you've probably dealt with in the past could just be simply the area of a circle, right? A little bit of geometry review for you. An area of a circle has a radius that can be utilized in the context of A, capital A, equals pi r squared. I made one up off the top of my head, a formula that you've used for sure in the past. As more commonly used in this particular context, what you will be using is a formula that uses 4 letters. And I'll explain in a moment what that entails. A formula is an equation that states a relationship between one quantity and one or more other quantities. Use the simple interest formula, capital I for interest, equals P principal times R interest rate times T time, and solve for T. The formula I equals PRT is a literal equation because letters represent both variables and known constants. Now I had earlier mentioned A equals pi r squared. R and A can be solved for if you know the other letter as a constant. And then there's other parts to that, for example, pi, that we attribute as just a simple constant. And that's unchanged, by the way, in that equation. In this particular equation, though, I equals PRT, based upon the directions in the problem, again, what equation can she use? Well, she will be using this. And in what way? Well, if we take a look, if we're solving for T, what we can do is take the equation and divide out the things that are essentially keeping T from being all by itself on the right side. So dividing both sides in the next step you see by PR. When you divide both sides by PR, the P's cancel or cross off or divide out technically, as do the R's. And therefore, if you see there in the next step, you do in fact have T all by itself. It's isolated, in other words, so that I, capital I, over P times R is equal to the time. So if you know the interest, if you know the principal, and if you know the interest rate, you can calculate time. You use properties of equality to solve literal equations for a variable, just as you do linear equations. So we are going to be dealing with certainly a lot of different formulas in this class. A linear equation is a very important version of a formula that we can utilize in various ways. And I believe if we look down below, it says when she writes the equation this way, she can use what she knows, like I indicated, I, P, and R, in order to calculate what she needs, which would be time in this case. Let's move on to example 2. So now we get to take a look at how maybe a problem can be solved, more specifically if we know some of those variables as a constant. Let's take a look. So in a half hour, Sarah is meeting her friends at the lake, 6 miles from her house. At what average speed must she ride her bike to get there on time? So let's start off. Step 1, solve the distance formula for r. Now, if you don't recall, or frankly, if you've never seen this before, I do need you to note very specifically that d, distance, equals r, rate, times time, t. And it notes that obviously off to the side there. An easy way to remember this, simply if you're talking about miles traveled, or the distance between 2 points of which maybe you are traveling in a bike or in a car or on a bike, that kind of thing. R would be the rate. Oftentimes you'll see for R units, for example, miles per hour. Pretty typical unit of speed or rate. And then T, time. So if you have miles per hour, for example, times hours, those units of hours cancel and you're left with a distance of whatever constant you get in miles though, as far as the units. So for this particular problem, again, is set up so that you are solving for r. As you can see, dividing this equation by t allows for this. So if you divide both sides by t, you have d over t equals r. Okay, great. That equation will be utilized in a moment. Step 2, find the average speed or rate at which Sarah must ride her bike to be on time. So again, using this equation, d over t equals r, knowing the distance, and again, reading the problem up above, we do know the distance to be 6 miles, and we know the t value, of course, 0.5. I do want to highlight that the half hour at the beginning of time, the half hour increment, we're going to use as a relation to hours. It's obviously 0.5. Half hour is 0.5 of an hour, or half of an hour. So again, because this d value is in miles, miles divided by hours is going to leave us with, if you do the math, 6 divided by 0.5, or 6 times the reciprocal, 6 times 2 yields 12. So r is 12. Sarah needs to ride her bike at an average speed of 12 miles per hour to get to the lake on time. Okay, it's important to note too, yes, we're solving for r, but r is in fact an average speed when it's all said and done. Is she going to maybe slow down or speed up at various points in time on her trip? Sure, she probably will. She'll have to if she has spots where there's rough terrain, that kind of thing. She's going to have to slow down and or stop, or speed up for that matter. But on average, from point A to point B, if she's traveling 12 miles per hour, she's going to get there on time. So example 3 continues the premise of working with formulas and or literal equations. So let's take a look. A worker at a framing store is making a rectangular frame. He knows that the perimeter of the frame is 144 inches and the length is 40 inches. How can he determine the width of the frame? Okay, so the perimeter is given of 144 inches, and that's important, obviously, as is the length. So what we need to do is consider how this is going to be kind of put together in the context of, well, as you can see, step 1, the rewritten version, or just writing a version that you may or may not already be familiar with regards to perimeter. So remember, perimeter is just adding up the sides of, in this case, the rectangle. So you have 2 widths, or 2w, and you'll see that here in the equation or formula. And you also have 2 lengths. Okay, so P perimeter equals 2L plus 2W. They do want you, though, in step 1, like a problem or two we've seen thus far, we're going to solve for W. So solve such that you get W by itself. Now the first step here is to subtract 2L, so that these are going to cancel on the right side, and all you're left then with on the right is 2W. And then you already see the next step unfold. I showed you kind of 2 steps here, so that if you divide both sides by 2, nicely enough, W is P minus 2L over 2. So if you know the perimeter and if you know the length, which technically you do from the beginning of the problem, right? You know 144 was the perimeter and 40 was the length. You can solve for W. The perimeter formula in terms of W is, all right, as such. Okay. So if I continue on with step 2, I already said this, of course, but step 2 says use the literal equation to solve for W when P is 144 and L is 40. I don't think that comes as a big surprise. We can now plug it in such that P, again, we know it's 144, L is 40. You can do that on your calculator and check with me, but 144 minus 2 times 40 all over 2 does in fact end up being, as you see now, 32. So it turns out the width would have to be 32 inches given the length of 40. And if you want to double check your answer here by adding 40 plus 40 plus 32 now and 32, or 2 times 40 plus 2 times 32, it will end up being 144 inches in perimeter. Example 4. Continuing on. According to Teo's bread recipe, he should bake the bread at 190 degrees Celsius for 30 minutes. His oven measures temperature in degrees Fahrenheit. To what temperature in degrees Fahrenheit should he set his oven? So this equation right here, capital C equals 5/9 quantity F minus 32. This is how you would go about converting Fahrenheit to Celsius. So if you know F, you can calculate C. So let's take a look and see how that applies on this scenario. So rewrite the formula to find the Fahrenheit temperature that is equal to 190 degrees Celsius. All right, so we're going to take the equation, step 1, solve for F. So actually, instead of using the equation up above, formula technically up above, we're going to rewrite it as what? Well, rewrite it such that F is isolated. So there's the equation. First step, you want to get rid of that fraction, so you can either divide by 5/9 or, as they show, multiply by the reciprocal, 9/5. In doing this, the right side is way nicer. As you can see, it just ends up being F minus 32, while the left side is now 9/5 C. I'll continue on, and if we see here now, to get F by itself, simply add 32 to both sides because you're already subtracting, right? F minus 32. Adding 32 will yield this literal equation such that F is equal to 9/5 C plus 32. Great. Step 2 is to use the formula for F to find the Fahrenheit temperature equivalent to 190 degrees Celsius. Okay, remember we said earlier that if you wanted to find Celsius, you can plug in F. Here, you know Celsius, so let's go ahead and find F using the new version of the formula, the literal equation technically. So there you go. There's our new version. We plug in 190 for C, and we do the math. So 9/5 times 132, times 190 plus 32, and there you have it, 374 degrees, and that is in Fahrenheit. So Teo should set the oven to 374 degrees Fahrenheit. So that concludes our notes for today. As I scroll down here, I wanted to ensure that you guys are comfortable with every once in a while noticing these try-it problems. It's not such a bad idea off and on for you to go ahead and practice doing those try-it examples, because they're I think very nice to follow up with any given example that we go through. I'm going to go ahead and ask that you continue with double checking your notes and cross-referencing those as you do your homework tonight.